All right, so going through how to find a derivative by graphing. If you haven't done so, open a new graph page. We graphed x squared, already done. So, and then I need to press the little, you see the key to the right of the 9. That's your template.
Yeah.
So you click on the template and then you click where it's D over D box of box. That's where I currently am at. This is the derivative template. Type X for the first field of the derivative template. So right here, I type X. Type X.
You type X in the first little D.
Yes, in a little box. Then if I continue, press tab to move to the second field. Type F1 of X or press var to see listed variables. So I could say F1 of X. I literally type F and 1.
Of X, and you just put your own parentheses for that?
Yeah.
Okay, where's the F? The little, why can't I type U? Wait, oh, there it is. I'm so lost right now.
Okay, so I'm gonna walk you through it again.
Cool.
Alright, so I have x squared, coolio. Now I go to my second function. I click on the template tab. I go over to where it says D box, boxy boy. And then check, oh my god, it disappeared. What did I do? This is, okay, and I click here. So I have the X in the bottom, and then I literally can type F1, or you can click the var key, variable, which is right next to delete. And it's like, what do you want to put? Oh, that's right, f of 1. And what is it? F of X. It's a function in terms of X, and I push enter, and then it graphs it. The cool thing with having this entered is if I go here and I change this to a cube, it shows me the derivative graph.
Oh, it still does it.
Yeah, I can change this to 6. Oops, hold on.
Where are we supposed to get that?
So if I say X, here's the derivative. If I go up here and change it, maybe I want this to be to the third power. Let's change it. I'm going to go up here. I'm going to put it to the 3 over 2 power.
Wait,
Ooh. What?
Mine don't show up.
What do you mean?
Like I put in the derivative and it just I see it show. It says it exists, but it like
All right, ready? The really powerful thing about this is I could put in any function here. Ready? How about x to the 5th? How about like -5, -6, whatever? Check it. Okay, so ready? Questions one at a time. I don't want 50 people asking. So I will say Abby first.
Well, I don't understand what you're.
Hold on. Shh. Okay.
I don't understand what you're doing. Like, I don't have a specific question. I know you want a specific one, but I literally don't know.
Okay. So this first one is a function. I'm just looking at x squared, which is the blue, and the red is showing me the derivative. The derivative is literally telling me. So the red, you had to push. Did you push the template tab? Okay. So if you are not there in your notes on page 8, this is what I'm following. Okay. So I'll delete this and I'll go through how to do that again. So I have equals. Oh my gosh, this is not what I want. Just a second. Menu, entry, edit, function. Okay. Okay, so I have x squared. I go to F2. I'm pushing the template tab, which is to the right of my 9 button. I go over to where it is D box. Oh my gosh. So in the bottom, in the bottom, I put X, and then right here, I'm wanting to do whatever my first function is. So either I can push variable, right? The VAR. Do you see the red key lit up? And it's like, hey, do you want to use the first function since you have it defined? And I'll say, you know what? No, I'm going to type it myself. So I say F1, open parenthesis, X, close parenthesis, enter. And then it will show me. So I could pick any point. Like, what about right here? What is this point right here? I could trace it. Like, oh, okay, so that's telling me at an x value of -1 for my original graph in blue, it tells me the slope there is going to be, well, what's my y value here? -1. It'll tell me the slope for any point. All right, so I can push trace. Just a moment. I'm going to push trace. Trace graph. Yeah.
I've never seen that. No way. Oh my god. All these years I've been doing
What? This is not like the goal of today, so.
But I think it's good that we're right.
Yeah. Okay. So if you push menu, trace graph, and then you push the down key, like check it. Look at this red. It's telling me when
But it's going too fast.
X when what?
Why was it moving so fast?
Because I was moving it. I was moving it away from everything else.
Yeah.
So this is telling me when I put in -1.2 for x into x squared, what is the slope for my parabola at -1.2? It's -2.4. What is the slope at -2.1? -4.2. So it's telling me the slope, which is the y, of my blue graph. Where? At the red, at the x of my blue graph. Okay.
That's crazy.
I have a question.
Yes.
When you're putting in like your derivative function, you know what I put in.
What? I didn't do it. My calculator did the derivative for me.
How do you know like you put in f11 of x?
Because that is where my function is. It's f1 of x. That's my first function. If I had an f3, let's say I put a new function here. Right, how about, let's subtract x to the 6. Just a moment. Nope, just a moment. Shh, just a moment. Okay, so ready? Come up here. I don't want it to be my first graph. I want it to be my third one. Now it'll show me the derivative of the third
So
function.
why is it just of x?
Because right now it's in terms of x.
So you do it.
All of my functions are in terms of x right now. My derivative is in terms of x.
So the type of graph that you have.
So for us, we're going to be doing it in terms of x for at least a couple more, maybe a couple weeks.
So the degree doesn't matter.
Degree, like to the 7th power and stuff. We're going to figure out how to deal with that later.
So right now it doesn't matter.
Right. Okay, question, Hannah.
Do derivatives flip? So like is the derivative of 2x, x squared? Or is that not how it works?
No, derivative of 2x is 2. Because if you graph, think about it. If you graph 2x, what's the slope? 2. Okay, so that's, I wanted to show you that way. And if we go to the other way of finding the derivative, come here. Let me go to the home. Let me go to calculate. So if I click menu, actions, wait, what did I say? Calculus, add calculator. Numerical derivative at a point. So variable x, value, let's say it's at 2, first derivative, cool. So derivative at a point. So that whatever x value I wanted to evaluate at, that's what I put. Now I can put in any function I want. Here I'm going to put x squared. What should the derivative of x squared be at x equals 2?
2x.
4. The derivative value should be 4, the slope value. So, let's go through it again. So, I'm going to go through it again. Ready? So, I click menu, go down to where it says calculus, and then I want the derivative, numerical derivative at a point. And it says, hey, what's your variable? X. We're doing it in terms of x. What value? X equals what? I don't know. Pick a number. Abby, what number?
7.
Any number. 4. Okay. 54, I guess. What function do you want?
I want x cubed.
X cubed? X cubed, okay. So it tells me for the function x cubed at x equals 54, this is what the slope of the line is, 8,748.
So what would the question be like the test would ask you?
So, for example, So you do have to show work. What I'm showing you right now. So I'm showing you is how you would do derivatives on a calculator. Maybe you're at home, whatever.
We can check our work.
This is how you check it and you make sure you're on the right track.
What happens if we don't know how to check?
This makes no sense. That makes no sense. Because up till now, you've been showing your work. If I show work while I do notes, you can show work too.
But then you know that I know how to do it if I really do it.
No, it's not.
Wait, so this is the question?
What? So there's, I just showed you guys the practice quiz. So if I'm asking you for the derivative at a point, oh my god. Okay, sometimes you guys drive me nuts. Ready? Here we go. Here's an example. Find derivative at indicated point. If you would, ready? We could type this in. Let's type it in and let's see what we get. Hold on, can you pause for just 1 second? Okay. Calculus, numerical derivative, let's see. X, what am I supposed to find it at?
It didn't work.
At 9. And I'm putting in square root of X. Look, 1/6. That's exactly what we get when we do it on our quiz here. How do you show work? Right here. Do you see this? Look. Oh my god. Look, I just showed you a way to double check your work. I just showed you a way to make sure you don't miss these two problems because it will literally tell you what it is. Okay. Alright, I'm over this. We're going to continue on. Goodbye. Goodbye.
Just trying to understand.
Okay. We're going on with the lesson. I've spent too much time going over this. Cool. Alright, differentiability implies continuity. Do you understand the calculator or have a question?
No, I'm just a question with the calculator.
Okay.
When you do the derivative on the scratch pad, how do you get the x equals?
So I click menu,
Uh-huh.
calculus, numerical derivative at a point. Variable is always x. Which point do I want it to be at?
I thought it was
4. Enter. And then whatever your function is, that's where you enter it, right there.
It's like you're going to a restaurant. Menu for one.
Cool. Sure.
You press menu for
Sure.
one.
Okay. Okay.
I'm not crazy.
I don't actually.
Alright, and
I go to restaurants by myself.
continue. We're continuing. So, differentiability implies continuity. If we have a derivative, if A has derivative, oh my gosh. Okay. So differentiability implies continuity. If something's differentiable, it means it's continuous, but it doesn't, but the converse is not true. Just because something's continuous does not mean it's differentiable. So an example is like a cusp, maybe absolute value. Those are continuous. They are defined for all real numbers, but they are not differentiable at x equals 0. Because for absolute value, you're approaching two different values. You go immediately from having a slope of -1 to 1. For a cusp, you approach negative infinity, and you're approaching infinity as your slopes. Like, no. Just because something's continuous doesn't mean it's differentiable. Okay. The graph of a function over a closed interval is given. At what domain points does the function appear to be differentiable? Continuous but not differentiable, and neither continuous nor differentiable. Okay, at what domain points? Literally, I'm asking for the x values. So for A, at what point does it appear to be differentiable? So it seems like I can take a derivative from -2 to 1. Let's see, to -1. What's wrong with -1? Of corner. Of a corner. I have a corner at -1. This is just like absolute value. And then I'm going from, let's see, union -1 to 0. What's happening at x equals 0? We have a jump. We have a jump at x equals 0. So union 0. What's the next thing we need to look out for?
Bracket 0 to
2, because it's undefined. It's undefined. I mean, it's a hole. Yeah, the function is undefined at that point. Well, I mean, it's defined under here, so it's a hole.
2 to 3.
Would
Isn't it?
you not
Yes.
bracket the second 0 to make to 2? So, you see what I'm
What?
talking about? Okay, would you not bracket these two?
No.
But they have the circle.
Well, I have a hole in the middle, so I can't include 2 because there's a hole. I can't include 0 because there's a jump discontinuity, and I can't include -1 because I have a corner. Those are literally the 3 x's I cut out. Okay, and B, where is it continuous but not differentiable?
2 to 3.
At x equals -1. There's only 3 points where it's not differentiable, where I can't take a derivative. That's because I had a corner, I had a jump discontinuity, and I had a hole. Alright, I literally had a discontinuity as I was traveling on my line. So, where's the place where it's continuous? Heck yeah, right here it's continuous. It goes down and comes back up.
Oh, but it's not.
But it's not differentiable. And then, what?
Differentiable means it has the same slope. Or what?
What?
Wait,
Differentiable means it has the same.
You're able to take a derivative.
I thought -1 is not. I thought -1 is not different.
It's not. So B is saying continuous but not differentiable.
Oh, BBB.
Wait, what is your question? I'm trying to understand it.
No, I just.
Wouldn't differentiable also mean that it must have the same slope throughout?
It doesn't have to have the same slope throughout. Differentiable means you're able to take a derivative.
But what is a derivative?
Someone had to say.
Thank you.
All right, what is differentiability? A function doesn't have a derivative, meaning you can't find a single slope for that point if the slopes of the secant lines fail to approach a limit as x approaches a. Meaning, as I approach it from one side and I approach it from the other, I should be approaching it where it's approaching the same slope. Not necessarily approaching the same number for function, but approaching the same slope. Here, if I have a discontinuity, guess what? I'm approaching the slope.
They're approaching the same slope, but they have the same slope.
The one-sided limit. So here,
Wait, would that be differential?
I don't have a derivative where I have a point of discontinuity.
So you can pinpoint it by it looking the same.
So this is showing the derivative graph. The example for this one I gave was the absolute value of x.
The first one was discontinuity, that would not be differentiable, right?
Right.
Yeah, I told you.
Corner. Look, the limit. Are we gonna be able to finish section 2? So today we're supposed to be finishing section 3. I appreciate questions. What I don't appreciate is you going off and having conversations that have nothing to do about this. So I'm not approaching the same slope from both sides. As I get closer from the left side, I'm like, oh, my slope will be -1 here. As I approach from the right side, I have a slope of 1. These are not the same. I have to be approaching the same slope from both sides. Now, my slope can be changing as I'm going throughout the function, but when I'm approaching one point from both sides, I have to be approaching the same slope. Here, remember how if I get closer and closer, literally these slopes go to infinity? Same way here, as I come up, my slopes get steeper and steeper till I have a vertical tangent, yes?
For vertical tangent, isn't it also differentiable? So I could both.
So it's continuous, but it's not differentiable. These are the 4 cases where it's not differentiable. These are the 4 cases where it's not differentiable.
Example. What? Just. Oh, okay. I don't get it. I thought you just said that if they're approaching the same slope, they're different.
So the first one, you literally have a discontinuity. So if you have a jump, it won't be a nice smooth slope.
So if it's any of these 4, it doesn't have.
Those are the 4 I gave you on your practice quiz to choose from. What's wrong, Shani? What's wrong? Do we need to like move seating charts? Do we need to like tell you guys how to behave and like how to like control it without having snide comments to each other? Okay. So the 4 cases where it's not differentiable is literally if you have a discontinuity, a jump discontinuity, you could have an infinite discontinuity, a hole. Those are any types of discontinuities. So this one example I think is a little misleading. Discontinuity means you have a hole, you have a jump, you have an infinite discontinuity. That's where it's not differentiable. It's just a discontinuity. Or you could have a corner, which is an absolute value. You could have a cusp where it's literally looking like a bird because you're approaching, the slopes are approaching a vertical, which is undefined. Here you have a vertical slope in the middle. Okay.
But none of those are differentiable.
None of them are differentiable. They will not have a derivative at that point where this is occurring.
What's that?
Huh?
Is there any, on what page can I find one that is differentiable? We don't have to do it as a class.
Yeah, so this one right here, this is differentiable.
So, okay, so how is that different?
So if I'm looking, it's defined everywhere. I don't have a discontinuity, right? If I had a hole, a jump discontinuity, or an infinite, it would not be differentiable there. There is no point in this graph where I have a discontinuity. This is not a corner. It is not a cusp. It does not approach a vertical slope, right? As I look at the slope here, slope, 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 it gets horizontal. So I'm drawing the tangent lines. Nowhere does my tangent go vertical, straight up.
So would it be fair to say, as long as it's not on this page, it's differentiable?
Well, these are the 4 cases where I told you these are where it's not differentiable. So if it's not a corner, not a cusp, not a vertical tangent, and not discontinuous, it's differentiable. Cool. Yes. All right. So C is asking, where is it neither continuous and it's not differentiable either? Well, where are my other 2 points of non-differentiability? X equals 0 and x equals 2. At x equals 2, I have a discontinuity at a hole. At x equals 0, I had a jump discontinuity. So it's not continuous. And because I have a discontinuity, it's not differentiable. Okay. So these questions on example 3, these are like the calculator okay problems. These are ones like I'm giving you on the quiz. So y equals x to the 4/5. What you can do is you can graph it and see what we get. So I go to my graph. I want x to the 4/5 power. What?
Top dog in the house.
Top dog in the house.
Top dog in the house?
Yeah, because it was like 4/5.
Got it. Got it. Got it. Okay, so if you look at this, what does it look like? It is a cusp. So it's a cusp. It says the function fails to be differentiable at x equals 0. Determine whether it's a corner, cusp, vertical tangent, or discontinuity. What about 1 over x? Without even graphing. Vertical discontinuity. It's a discontinuity. Literally, it's 1 over x. Let's graph this. 1 over x. What's happening at x equals 0 is a infinite discontinuity. In discontinuity. Awesome.
Wait, what did you do for the value for the last one?
I just did x to the 4/5, and this one I just did 1 over x. Okay. Find all values for x which the function is differentiable. Meaning, why don't we talk about where it's not differentiable? And it wants all values, aka we want the interval. If I ask you for the
Domain.
Do you want me to go back to the calculator? Okay. So, let's see. This is the same thing as saying x minus 1 and x plus 1. Right? I know both of those cannot equal 0. So that tells me there's 2 points where I'm going to have vertical asymptotes, which are discontinuities. Exactly, because when you have a rational function, just look where the denominator equals 0. We're trying to find all the places it's differentiable. So what we can do is list out the parts where it's not differentiable. Where is it not differentiable? We have a discontinuity. Here, we have a vertical asymptote. We have a vertical discontinuity at x equals 1 and x equals -1. All right, so x cannot equal 1 and x cannot equal -1.
So what were your answers?
This.
Okay.
So when I'm trying to find where it's differentiable, we just cut out the places where it's not differentiable. So we cut out all the places where we have a corner, a cusp, a vertical tangent, or any of the discontinuities. Vertical discontinuity, jump discontinuity, which is a hole, or we have a infinite discontinuity. Those are the points where you cannot be differentiable. Okay.
Is this differentiable nowhere? Like, because it's an odd root. Like, there's nowhere.
It's differentiable everywhere.
I mean,
So if you have a cube root looks something like this.
yeah.
But
Be a linear, right? A linear.
But in the middle, there's a vertical discontinuity. Where is it occurring at?
0. No, 3. Negative.
So when you have an odd root, this part underneath, wherever that's equal to 0, that's where it will not be differentiable.
So x equals 2. You ignore the.
Right, because that just shifts it up and down. So if I take x minus 2 equal to 0, I see at x equals 2, this is where it will not be differentiable because that's where I'll have a vertical tangent, right? That's where I'm hitting this point right here and it looks like I'm having a vertical tangent at that point. Okay, so if that's the place it's not differentiable, all I have to do is list out everywhere that is not that point. Beautiful. Literally, what I'm trying to do is list out all values of x where it's differentiable. So as long as we exclude, cut out the values of x where it's non-differentiable, we'll be good. And lastly, the intermediate value theorem for derivatives. If a and b are 2 points on an interval where our function is differentiable, literally that means at every point you can take a derivative. You have a single slope for every single point. Solid. Then the derivative graph takes on every value between the derivative at a and the derivative at b. Okay, what the heck does this even mean? Let's say this is a, and let's say right here this is value b. So if you look at the slope right here, I need to pick b to be a little different. Let's have this be b. So I'm looking at the slopes. A has a slope of 0. B has a slope of, well, half something. All the derivatives, all the slopes in between them will be between those two numbers. So if I'm going from 0 to a slope of, I don't know, let's say this is like 2 or something. That means that all the points in between them, the derivative takes on every value between 0 and 2. It like smoothly switches over. That's the IVT, intermediate value theorem. This derivative takes on every value between the two endpoints derivatives, between 0 and whatever number it was. So remember, derivative is literally the slope of your tangent line of your function. So when I have a function, right, the derivative function is literally telling me, here's the slope. You can pick any point and it will spit out whatever the derivative is. Great. Cool. Okay, well, literally, school is over. So after we're done with the quiz tomorrow, we will go through as much of 3.3 as possible. Cool.